Welcome back everyone. In the last few lectures, we had been seeing how to design state feedback controllers for systems, whether it be for CISO systems or CISO controllable systems or CISO uncontrollable systems. Today, we would be looking into state feedback for MIMO systems. Let us dive into that. For a CISO system which is controllable, we know that the state equation x dot equal to ax plus bu can be transformed into a state space equation of this form using a suitable transformation map. And we also know that once we get from this state equation to this new form, we can easily design a control law of the form u t equal to minus k hat z such that I can change the coefficients in the last row of the state matrix to something that we desire. Today, we will extend on this same idea, however, we will do it for the MIMO case. Now, in case of a MIMO system, this B will be n cross m and A remains as n cross n. So, if I find out a suitable transformation map, the new state equations that you will get can be taken to this form. This looks quite a complicated form, but if you see, if you mask this part, then notice that this part and this part is exactly similar to the controller canonical form for the CISO case. Now, for the MIMO case, the controller canonical form becomes this. What is important to note here is that the terms here are all zeros, okay? Only the last row here have some values. Similarly, the terms here are all zeros, the last row has values. The diagonal blocks here, the diagonal blocks that you can see here are in controller canonical form, okay? And the B matrix also has a nice form. You can see that this is like the controller standard controller canonical form B matrix for the CISO case, and then at the bottom everything is 0. Similarly, for the next column also, this block is a 0 0 1 vector like in the standard CISO case. The bottom part are all zeros, and at the top all these terms are zeros except this. So, in the same way we can go ahead and get a B matrix in the transformed form, and this form here, this being your A hat and this being your B hat, is the controller canonical form for MIMO case. Now, the question is, how do I get to this form? If I get to this form, how does it help us in changing the eigenvalues of the system? For the CISO case, remember, once we got to this form, using this B matrix, we were making the K matrix so that the row here gets changed. Now, suppose I take a simpler case where I have a hat matrix which is 5 cross 5 and my B hat is of 5 cross 2, that means it is a 2 input system, and suppose I somehow got to the controller canonical form which is of this structure. You can notice that it is exactly following the structure that I have shown here. So, this is becoming 3 cross 2, 3 cross 3, this is a 2 cross 3 matrix. So, you can see this is 3 cross 3, this is 2 cross 3, and then you have this part which is again a 3 cross 2 matrix, and this part is a 2 cross 2 matrix. This is what we are getting, and in the B hat also it is following the structure that I have shown just now. Now, if this is your A hat and B hat, of course, I have not told you how to get to this structure, I will tell you that, but suppose I have got to this structure, then how does it help us? Suppose I use a control law of the form u equal to minus k hat z. Remember, I have converted x dot equal to ax plus bu to z dot equal to a hat z plus b hat u, where this is my b hat and this is my a hat. Okay. And now, here I am applying this control law u equal to minus k hat z. It is exactly similar to what we were doing for the seesaw case, and say k hat is a 2 cross 5 matrix here. Why will be k hat a 2 cross 5 matrix? This is a 5 cross 2 matrix, b hat is a 5 cross 2 matrix. So, k hat better be 2 cross 5, so that when b hat multiplies with k hat, you get a 5 cross 5 matrix, because at the end, after you have applied the control law, the system equation will become something like this. And this we have been doing a lot. In the last few lectures we have done this. So, you understand that k hat must be 2 cross 5. So, I am saying that the elements are these. Now, if I apply this control law, then a hat minus b hat k hat will come out to be this. When I multiply this part out, I will get something like this. Okay. Notice that since there are zeros here, the top rows are zeros. Since there are zeros row here, this row is 0, and then we have 0 1. So, 0 times of this row plus 1 times of this row will give me the last row. So, this multiplication you can do it on your own. So, you will get a multiplication of this form. Now, important to note here is that the top part is 0, which means this part, when they will be subtracted, will not get affected. Similarly, this one will not get affected. Okay. So, what do we get after the subtraction? This is what we get. Okay. So, this is the structure that we are getting. Important thing to note here is that K1, K6, K2, K7, K3, K8, K4, K9, K5, K10, all these are changeable. That means, I can take any value I desire in those points, which means these values can be assigned arbitrarily whatever I want to, right. So, let us go ahead and see how does that help us. Now, since this is my a hat minus b hat k hat expression, now notice that if I take k6 to be equal to minus b naught beta naught, then this term will go to 0. Similarly, if I take k7 to be minus b1, this goes to 0, and k8 to be minus b2, this goes to 0. So, this will be the expression if I choose k6, k7 and k8 to be this. And the good part about this expression is that now this has become a block upper triangular matrix, and what happens if it is a block upper triangular matrix? The eigenvalues of this matrix are the eigenvalues of this matrix union the eigenvalues of this matrix. I had already talked about this earlier also, that if you have a block upper triangular matrix or a block lower triangular matrix or even a block diagonal matrix, then the eigenvalues are nothing but the union of the blocks sitting on the diagonals. So, union of the eigenvalues of the blocks sitting on the diagonal. So, the eigenvalues of this union the eigenvalues of this will be the eigenvalues of this matrix. However, notice importantly that the block matrix here is in a nice form. This is the phase variable form, which means just by looking at the matrix, I can write down what will be the characteristic polynomial of this matrix. The characteristic polynomial will be, for this green part, will be given by this part. You see, this is 3 cross 3. So, this will be the characteristic polynomial of this part will be of degree 3, and you can see that we will have s cube plus alpha 2 plus k 3 minus L naught b naught s square plus alpha 1 plus k 2 minus L naught beta 1 s plus alpha naught plus k1 minus L naught beta naught. So, this the characteristic polynomial of this part is given by this, and the characteristic polynomial of this violet part will be given by this violet part. And now, since I have the characteristic polynomials, I just have to carefully choose the values of k3, k2 and k1, k10 and k9 here, so that I can make it the desired polynomial for our pole placement or for our eigenvalue assignment problem. So, question is, how do I get to this T matrix? I will take an example to show you exactly how we can choose this k1, k2, k3, k9, but before that let me tell you the algorithm by which you can find out the T matrix to get to this nice controller canonical form for the MIMO case. So, the idea here is, see, I am not going to prove this algorithm, I will just give you the recipe. You can go ahead and look it up in a book what the proof is like. I will just tell you how to get to the controller canonical form for the MIMO systems directly. So, the idea is, first you see, let me name the columns of B to be B1, B2 to be M. Since it is a MIMO system, I will have M number of columns of B, and then you create a non-singular matrix using the columns of B. How? Basically, you choose B1 first, then you append AB1 to it and check what is the rank of this matrix. Remember, this is a n cross 1 vector, this is another n cross 1 vector. So, if the rank of this matrix comes out to be 2, so this will be a matrix which will be an n cross 2 matrix. If the rank of this matrix comes out to be 2, that means that these two are linearly independent. Then you have to append another vector here, a square b1, and then check whether b1 ab1 to a square b1 is linearly independent. Again, remember, this becomes an n cross 3 matrix now. So, the rank of the matrix should come out to be 3 if they are linearly independent. If they are not linearly independent, the rank will come out to be 2 again, which means that this will become dependent. So, I will stop at this point and then I will introduce b2 here. And then again I continue to check whether B1, AB1 and B2 are linearly independent. If they are linearly independent, I will add the next vector AB2 here, check for the rank again, are they linearly independent. If they are not linearly independent, I will remove this and then I will add B3 here. And this I will keep on continuing till the rank of the matrix comes out to be n. Okay. So, remember, controller canonical form is only applicable when we are dealing with controllable system. So, since the system to start off with is controllable, the rank of the controllability matrix CAB must come out to be n, which also means that you will always be able to find out these vectors such that this matrix that you are forming will have a rank n. You will always be able to do that. If you are not able to do that, that means the system AB to start off with is not controllable. So, here is the recipe. You create a L matrix in this way. You keep on adding or appending vectors using B2, AB2, AB. In this way, you keep on appending vectors till you get a n cross n invertible matrix. Let me show you this with the help of an example. Here are your A and B matrices. So, once you have the A and B matrix, you see, I will now go ahead and write down the first column of B to be B1 and name the second column of B to be B2, and now I will go and check the rank of the controllability matrix A comma B to ensure that this system is controllable. Since the rank came out to be 3, this is a controllable system. Next, I find out the rank of B1, then rank of A into B1. So, the rank has come out to be 2, which means they are linearly independent. Again, here if you go back, you see the rank of B1, AB1 and A square B1 came out to be 2, which means this third column that I have just now appended is dependent on B1 and AB1. So, I will remove that column. Remember, so this is in this case n is equal to 3. So, I have to continue till I get the rank here to be 3. So, let me continue that. So, now I will remove A square B1 and put B2, and now you can see that the rank has come out to be 3, and we will call this matrix that we just now found out B1, AB1 and B2 to be my L matrix. And this is an invertible matrix here, because by the procedure that we have found out the L matrix, we have ensured that this matrix is invertible. Fine. Now that the matrix is invertible, now let us go to the second step. Now, the second step is definition of a quantity sigma k. How is sigma k defined? Sigma k is the summation of I equal to 1 to k mu I. So, that means that sigma 1 is nothing but summation of I equal to 1 to 1 mu I, which means this is mu 1. And what is mu 1? Mu 1 is this, right. So, in the example that we took, remember we took B1 first, then we went for AB1 and then we stopped, right. At A square B1 we had a dependency, so we stopped here. So, in this case this is your mu 1. So, in this case mu 1 minus 1 is equal to 1, which means mu 1 will be equal to 2. Okay. So, that means sigma 1 is nothing but 2 for our example that we had taken. Okay. What will be sigma 2? Sigma 2 will be equal to mu 1 plus mu 2. Now, what is mu 2? Mu 2 is this quantity. Again, what did we take? We took B1, A1, A B1 and then we took B2. So, this was our L matrix. So, in this case mu 2 minus 1 is 0, which means mu 2 is equal to 1. So, that means this becomes 2 plus 1 equal to 3. And now you can stop, because here we have reached the end, that means 3 we have reached, n was equal to 3, since we have reached 3. So, we can stop here. So, sigma 1 is 2 and sigma 2 is 3. Now, let me write it down here. Sigma 1 is 2 for us for the example and sigma 2 is 3. So, now in step 3 we will write Qk to be the sigma kth row of L inverse. Remember this L that we had found out. So, this L is an invertible matrix. So, which means that I can invert the matrix L inverse and I will get a 3 cross 3 matrix in this case. Now, what is Q1? Q1 is the sigma 1th row of L inverse. So, but what was sigma 1? Sigma 1 was 2. So, that means I am talking about the second row of L inverse. What is Q2? Q2 is the sigma 2th row of L inverse. What is sigma 2? 3. So, I am talking about the third row of L inverse. Okay. So, K was from 1 to 2 in this case. So, I do not have to go more. So, I can stop at this point, and now in step 4 you will use the Q1 and Q2 that you got to create this T matrix. And what is this T matrix? This T matrix for our example is Q1, Q1A and then Q2. So, this will be the T matrix, and this is the T matrix that will help you get to the transformation, and the transformation here is Zt equal to Txt. Remember, in most of the cases we are taking T to be equal to Q inverse, something like that, but in this case Zt equal to Txt we are taking, not Zt equal to Xt. Okay. So, remember the transformation that we are taking is Zt equal to Txt. If I take this transformation, I know that x dot equal to Ax plus Buu will get transformed into Z dot equal to Ta T inverse Z plus Tbu. So, this will be your A hat and this will be your B hat. So, let us look at the example that we took and see the algorithm again. So, this was my L matrix. Now, I will find out inverse of L matrix. I am calling that to be INVL. So, this is the inverse, then Q1 is the second column of the inverse of L matrix. So, I will take the second column. So, Q1 is the second column and Q2 is the third column of the inverse L matrix. So, this is the third column. Now, we will create the T matrix as Q1, Q1A and Q2. So, this is my T matrix, and now you will see that if I find out the A hat or A nu, that is T A T inverse, you will see that it will come out to be in this nice form, and B nu is T into B. So, this will be your B nu, and so now notice that this A hat and B hat, which we are calling A nu and B nu in MATLAB, but here you can see that this is in that nice structure that we were talking about. You can see this. So, this is in that nice structure we talked about, okay, and this is the controller canonical form for the MIMO system that we have. Now, we take this problem, you can see x dot equal to x plus bu is given to us, and we want to place the eigenvalues of the system at -1, -2 and -3. This is exactly the problem that we had taken, I had shown you in MATLAB. So, what we can do is we can get to the transformation matrix. We had just now seen how to get to the transformation matrix, take it to the controller canonical form. So, this is the controller canonical form that we got, and now what we will do is we will try to place the eigenvalues of this system at -1, -2 and -3. So, to do that we will use the control law, this control law, and once we use this control law, we plug it in here, we will get an expression of this form, okay, and then if you plug it and see it, now you can notice that this is the expression that we get. Now, what you can do is you can change this K4 to be 0, this K5 to be 0. Once you do that, notice that once you take K4 and K5 to be 0, system becomes this, okay, and you can see now I just have to choose K1 hat, K2 hat and K6 hat carefully, so that my eigenvalues get placed at -1, -2 and -3. Now, if I want my eigenvalues to be at these points, then I know that the desired characteristic polynomial must be this, okay. Now, what I can do is I can say that, okay, let us take the value of K1 and K2 to be such that the characteristic polynomial of this part becomes equal to s plus 2 into s plus 1, and the characteristic polynomial of this part becomes equal to s plus 3. You can choose it in a different way also. You could have said that no, let us choose the value of K1 hat and K2 hat such that the characteristic polynomial of this block becomes s plus 2 into s plus 3, and for this block it becomes s plus 1. So, it is a choice you can make, you can come up with your own K matrix depending on the choice that you are making. So, I am choosing to make the characteristic polynomial of this part to be this. Now, if the characteristic polynomial of this part needs to be this, so this part needs to look like 0, 1, -2 and -3, right, and that must be equal to 0, 1, -3 minus K1 hat and 4 minus K2 hat, which means that K1 hat must be equal to -1 here and K3 hat must be equal to 7 here, so that we get this as the characteristic polynomial for that block, and for this part I want this part to be equal to -3. So, which means K6 hat must come out to be 5. So, if I take K1 hat to be -1 and K2 hat to be 7 and K6 hat to be 5, then I will get my desired characteristic polynomial. Remember, K4 hat and K5 hat were 0. So, now I can change these values because I know the values. Only thing that I have not found out yet is K3 hat, okay, and you will notice that K3 hat will not affect much. I can choose anything for K3 hat because in this entire expression K3 hat was not showing up anywhere, okay. So, I can actually go ahead and choose K3 to be anything because that is not going to influence our characteristic equation in any form. So, I am choosing K3 hat to be 0. Now, if I use this control law, then this is in Z. So, I have to go back to X. So, I am using the transformation, and once I use the transformation, this is the control law that you are getting. So, this is your K matrix that you are getting. Let us look at this problem again, and let us see the control law that we came up with, does it help or not. So, we are finding out K hat first, which is we are writing K hat first, which is in the Z variable. Okay. So, this is the control law in Z variable, and you notice that A hat minus B hat into K hat will have eigenvalues exactly at -1, -2, -3. Now, the actual K is given by, so the actual K will be given by K hat into T. So, this is the actual K, and you can see that eigenvalue of A minus B into K will exactly come out to be -1, -2 and -3. Now, I can actually go ahead and change K hat. See, this K3 hat here was arbitrary, right. I chose a 0 there. Instead of that, I can go ahead and choose anything. So, I have chosen 1000 there. So, K hat becomes this, K becomes this, and now also even if you check A minus Bk's eigenvalue still remains at -1, -2 and -3. So, this choice is up to you, but of course, you should make this choice sensibly, because these are the parameters which gets multiplied with the states. So, if you choose a very high number here, that will multiply with the state to give a very big number. See, physically you are actually putting this back into the system, right. So, if you are putting this back into the system, when you have a very big number multiplying with the signal, the output of the block will also be a very big number. So, it might become a problem. So, if you look at the state diagram that we had, so this is how the blocks are connected. We had seen this earlier also, and as I was telling, you see this K is getting multiplied with X here. So, if you choose the variable that you can choose arbitrarily, for example, the K3 hat that we had just now chosen, that will multiply with a signal from this point, and this will go back into the system. So, if it is a very big number, then it will multiply with that state variable to give a very big input to this system, which the system might not accept, because these are physical systems, they have their boundaries. So, they cannot take as input after a particular value. So, there are constraints, input constraints on the system. So, you should not violate that. So, choosing those variables which are free, basically you can choose anything for those variables. You have to think about choosing those practically for your system, and then only you should choose those. Thank you.